Okay, good morning, all the students. Why are they joining late today? Any placement is going on, Nasma?
No, ma'am. No placement classes.
Oh. Okay, let's now start our third lecture under this module. In the last sessions, we have seen basics of sampling theory. Under that, we have gone through various terminologies like random variable, binomial distribution, normal distribution, what is an estimator, what is the mean of the estimator, what is the variance of the estimator, what is the standard deviation. Lots of such terms we covered in the last session. Okay, they provide us the basic information or the basic idea about the terminologies used in this statistical or sampling theory. In today's class, we are going to cover error estimation and estimating binomial proportions and the binomial distribution. How they can be used in sampling theory, we are going to relate. Now, what is error estimation and estimating binomial proportions? How does the deviation between sample error and true error depend on the size of the data sample? Now, you know what is a sample error, right? From a larger population, if you draw some sample, means if you draw some data points at random such that one draw doesn't affect the other draw. One draw is independent of the other draw. Right? In such way, if you take a sample, say this is the total population, from that you take a sample S, then what is the error associated with the sample and how does that influence the true error associated with the population? Okay, that we have tried to understand up to some extent in the last session. Now we'll understand that in more detail. Okay, now how does the deviation between sample error and the true error, means the difference between the sample error and the true error, depend on the size of the data sample? Does the size of the data sample have any effect on the difference between this sample error and the true error? Let us see. Now this question is an example of a well-studied problem in statistics. This is of interest. Why? Because many machine learning models have to most of the machine learning models have to perform well with the larger population as good as they performed with the sample, right? So whenever they are giving good accuracy with some sample, they should be generalizable. The model should be generalizable to the larger population also. Means if they're performing well with the sample, the same accuracy should be shown. At least almost the same accuracy should be shown with the population, larger population also. Then we say that machine learning model is highly generalizable. Okay, it has learned very well from the training data and it is able to predict properly with the unseen data or new data point also. In that case, we say that there is less deviation between the sample error and the true error. That is the error related to the population. That is the error related to the unseen data or new data instances given to the machine learning model. Okay, so this is the question of interest and it is well studied in this area of statistics. Now it is the problem of estimating the proportion of a population that exhibits some property given the observed proportion over some random sample of the population. So if you take some random sample from the population, whether it is exhibiting a property which can also be observed with a larger population, that we are going to study. Did you understand what I'm saying? We are observing some property with the sample. Now, are you able to observe the same property with the larger population? That is the problem of study. In our case, the property of interest is that H misclassifies an example, means H is giving some prediction error. Okay, that property we are going to study. Now, when we measure the sample error, we are performing an experiment with a random outcome. Do you oppose with this statement? Random outcome means what? I have already given you an example of random variable. Random variable is the variable which is expecting some random outcome. You don't have any idea about the outcome. You're not sure about what would be the outcome of that particular experiment. Now, when I toss a coin, you're not sure whether it would land on a head or a tail, right? In that case, we call it as a random variable because the outcome is random. The outcome is not, we can't estimate the outcome with some certain amount of confidence, right? In that case, we call it as a random variable. Whereas I have given you the example of deterministic variable. Deterministic variable means if you take if you're given the date of birth and if you're given the current year, you can calculate the age of a person, right? In that case, we call it as deterministic variable because you can calculate something with complete confidence, right? So the random variable's outcome is not predictable. You can't predict it with 100% confidence like you do in deterministic variable case. Now, when we measure the sample error, we are performing an experiment with a random outcome. Why? Because you are randomly picking some sample from the population and you are calculating that sample's error. Now, you pick another sample from the population. The sample error may be different from the first sample. It may not be drastically different, but it may be slightly different from the first sample. We first collect, let us see how it works. We first collect a random sample S. Let us take the random sample denoted by S of n independently drawn instances. Now we are drawing n instances from the sample randomly. You're picking each of the data point randomly without having any effect on the next pick. Right? Now let us take such kind of random sample S containing n independently drawn instances from the distribution D. Why we are saying from the distribution D? All of them adhere to some property. Okay, they adhere to some kind of distribution. They adhere to some kind of sequence in the data. That is why we are saying from the distribution D. And then measure the sample error S of H. Now, from the sample you have taken, measure the sample error. Means that is given to a machine learning model. It is trained with a algorithm. It is trained with an algorithm and see how much error it is giving. Okay, say it is performing with 95% accuracy. Its error would be 5%. Right? Now, if we were to repeat this experiment many times, not one time, if you are repeating this experiment many times, each time drawing a different sample SI, you're not sticking to the same sample. Whenever you're carrying on this experiment many times, in each experiment, you're taking a different random sample. Okay? Each experiment is containing again n data points or n sample points or n instances. Okay? Now, in S1, say sample 1, you have taken n instances. Again, you're taking a different sample in the next experiment, and that also contains n instances. Now you have taken another sample S3 containing again n instances. Each time you are taking equal number of data points for the sample, but picking it randomly. Means you are not sure that the sample contains same instances. You are picking it randomly. Now we are repeating this experiment many times, each time drawing a different sample S of I. S1, S2, S3 and so on, S of I of size n. Each of them is of size n. We would expect to observe different values for various sample errors. And the outcome of such experiment is a random variable. Did you understand? Each of these samples error is denoted by error Si of H. And we can observe that all these samples will have different sample error. Why? Because they are drawn at random. You're not drawing the instances according to a particular rule. Okay, you're drawing them at random. That is why their sample errors may differ whenever the sample error for that particular sample is calculated. Okay, and the outcome of such experiment is a random variable. The outcome of this sample error is not predictable, right? Each time you draw a sample, its error may differ. The sample error may differ. That is why we are calling it as a random variable. Whenever the outcome is not predictable, you call it as a random variable. Okay. Now imagine that we were to run k such random experiments. We are running this experiment k times, each time drawing a different sample having the same number of instances n. Now measuring the random variables, how to measure the random variables, now how to represent the random variable, that is the sample error you are calculating. You are representing it as error S1 of H, sample error associated with sample S1, error S2 of H, sample error associated with sample S2, and error Sk of H, that is the sample error associated with your kth sample. That is given as error Sk of H. You have represented all the sample errors by these notations. Now imagine further that we then plotted a histogram displaying the frequency with which we observed each possible error value. Say we are plotting a histogram. You know what for a histogram is plotted, right? Say sample error, 1% sample error is observed these many times, say 2 times, 4, 6, 8 and 10. Let us take a simple graph like this. Now 1% sample error is observed 2 times, 2% sample error is observed 4 times. Then most of the time 5% sample error is observed. Most of the time sample error 3 to 6. Let us take a interval. 3 to 6 is observed, and other times even more sample error is also observed, say 8% or 10%, like this. So what we are trying to model here, you are taking the error on the x-axis and number of times that error is observed with the samples is plotted on the y-axis. Now you can observe that as you go on increasing the number of experiments, remember I'm highlighting this word, as you go on increasing the number of experiments, when you increase the number of experiments, you tend to see that most of the sample errors fall between 5 and 8, and very less number of samples errors fall either on the lowest range or on the highest range. Okay, this is how you can observe the sample error distribution. Okay, so what you can notice here, it is following a form of normal distribution. If you perform your experiment very less number of times, the variation in the sample errors may be high. But if you go on repeating this experiment many times, then you can notice that the sample errors are assuming a normal distribution. Did you understand? Means most of the sample errors fall between a nominal range, say 5 to 8 or 5 to 10. But very less number of sample errors will show very high accuracy, very less error or very high error. Okay, so it tends to follow a normal distribution. This is again an assumption. We are assuming that as you go on increasing the number of experiments, in this case it is k, then we can observe that sample errors tend to follow a normal distribution. If at all you plot a histogram between the sample error and the number of times that sample error observed with the samples, right? Now as we allowed k to grow, that is what I said, if you keep on increasing the number of experiments, then the histogram would approach the form of distribution shown below. It can be seen like this. This describes a particular probability distribution called the binomial distribution. We can also call this as binomial distribution, where you have taken the number of data points in each sample as 40 and the probability of observing a sample error is 0.3. Now when you plot this graph, it shows a binomial distribution. And it is like also a inverted bell curve. That is why we also say that it is following a normal distribution. Okay, but now we'll focus on what is this binomial distribution. A binomial distribution gives the probability of observing R heads, number of heads, R heads in a sample of n independent coin tosses. Say, if I am tossing a coin 10 times and the probability of observing 6 heads are equal to 6 here, 6 heads, then this binomial distribution gives the probability of observing that 6 heads out of 10 independent coin tosses when the probability of heads on a single coin toss is P. You are taking the probability of a single coin toss. What is the probability of showing head on it? Okay, that if you are taking as P, then it is defined by the probability function P of R, that is the probability of observing R heads out of n coin tosses when P is the probability of observing the head and 1 minus P is probability of not observing the head. Okay, you know this according to probability definition. P is occurrence of the event and 1 minus P is non-occurrence of the event, right? In that case, if you take P as probability of getting head on a single coin toss, okay, means that is the occurrence of event you are interested in, and R number of heads are observed out of n coin tosses. Now, how can you write that probability function, which is also called as binomial distribution? How can you write that? It is nothing but n factorial divided by r factorial into n minus r factorial multiplied by, see this carefully, probability to the power of r, P to the power of r. What is P here? P is the event you are interested in. That is probability of head in a single coin toss. Now you are observing R such heads. That is why it is P per R. And you are also, it is same as not observing the tails. Observing the heads, probability of observing the heads is P. Probability of not observing the heads is 1 minus P. That is nothing but probability of observing tails. Okay. So out of 10 coin tosses, if you observed 6 heads, then the probability of heads is, say, you're taking R as 6 and you're taking n minus R as the probability of observing tails, that is 4 out of 10. Okay, that you are giving here. Probability P is the probability of observing heads in a single coin toss, and how many times it is observed? R times. The probability of observing R heads, the number of times heads has appeared is R. That is why it is written as P power R, multiplied by number of times tails are observed. Tails are observed means it is not the probability we are interested in. So it is 1 minus P. And how many times it is observed out of n? Out of n, you subtract the number of times heads are observed, that is R. So it is n minus R. That is the binomial distribution formula. This is how you can write the binomial distribution formula. N factorial, number of coin tosses factorial, divided by number of times heads are observed, R factorial, and number of times heads are not observed, that is n minus R factorial, multiplied by P power R. P is the probability of observing head in a single coin toss, and how many heads are observed? R. So it is P power R multiplied by 1 minus P, number of times tails are observed, that is 1 minus P, to the power of n minus R, number of times tails are observed. This probability is raised to power of number of times tails are observed. Okay, this is how you write the binomial distribution formula. If the random variable x follows a binomial distribution, Now, if this random variable x in k repeated experiments, if it is following a binomial distribution, then the probability of x taking up the value of r means what is the probability of observing r heads in n coin tosses? What is the probability of observing 6 heads in 10 coin tosses? That x will take on, that is what is given here, the probability of x equal to r, that it takes head, that x will take on the value r, that is 6 times for in our example, is given by, how is the probability given? Probability of r. That is why we are writing it here, probability of r. You're trying to find out what would be the probability of 6 heads out of 10 coin toss experiments, or what is the probability of 8 heads out of 10 coin tosses experiment. Got it? So that probability of number of heads that can be seen in n coin tosses, that is represented by this formula. Now the expected or mean value of x. X is random variable, right? Because you are expecting some random outcome. Whether it is head or tail, you are not sure of. That is why the expected or mean value of this random variable x, which can be denoted by E of x, that is mean of x, can be represented as n into p. N is number of coin tosses multiplied by p is the probability of getting heads on the single with a single coin toss. Okay, that can be represented as n into p. N is the number of coin tosses and p is the probability of observing head on a single coin toss. Now, how is the variance explained? Variance of this random variable x is np into 1 minus p. What is the deviation of heads occurring and tails occurring? You just multiply them. N into p into 1 minus p. 1 minus p is the probability of occurrence of tails. P is the probability of occurrence of heads. Okay, so the variance of this random variable, the variance you can notice in the 10 coin tosses can be explained by n into number of coin tosses into the probability of observing heads multiplied by the probability of not observing heads. That is nothing but probability of observing tails. Okay, that will give you the variance of x. Now the standard deviation of x can be given as square root of this variance. You already calculated the variance, right? Now this variance square root will simply give you the standard deviation. Okay. Now for sufficiently large values of n, that is, if you increase the number of instances in the sample and you increase the number of experiments, that is number of samples you have taken. Not only the instances in the sample, but also the number of samples you have taken. If you keep on increasing the number of experiments, in such cases, for sufficiently large values of n, the binomial distribution is is closely approximated by a normal distribution. This I have been asserting from the beginning of the class, right? The binomial distribution, if you take the binomial distribution and try to increase the number of experiments and also the data points in each experiment, in such cases, it is closely approximating a normal distribution. You can see that the entire outcomes, the sample errors you find across these samples will assume a normal distribution. That is in the form of a inverted bell curve. Now, a good way to understand the binomial distribution is to consider the following problem. Let us take a simple problem and understand this more better. Now, you are given a worn and bent coin, some coin, say coin you have observed, which is not fair coin. Then I say fair coin, it is not biased. When you toss that coin, when you toss a fair coin, then you can have chances, 50% chance of getting head and 50% chance of getting tail. But whenever you're given an unfair coin, say a worn out coin, bent coin, then it is having some bias. It may always land on more times on head, less times on tail, or more times on tail and less times on head, like that. Okay, when I say it is an unfair coin or not fair coin, then it is having some bias with respect to the outcome expected, right? Now you are given a worn and bent coin and asked to estimate the probability that the coin will turn up heads when tossed. Let us call this unknown probability of heads as P. Okay, let us take the probability of getting heads in the coin toss with this unfair coin is P. Now you toss the coin n times. Okay, toss the coin n number of times. You are repeating the coin toss n times and record the number of times R that it turns up head. Okay, so what is R? The number of times you observe head out of n coin tosses. Say you observe 5 heads out of 10 coin tosses, then R equal to 5. If you observe 8 heads out of 10 coin tosses, then R equal to 8, right? Now, a reasonable estimate of P is, how do you calculate the probability? R by N, right? How many times you observed heads? Say 7 times. Out of how many coin tosses? 10. In that case, you can say the probability of observing heads out of n coin tosses is 0.7. Out of 10 coin tosses is 0.7. Okay, that is simple calculation, right? How to calculate the probability? Number of outcomes by total number of number of outcomes you are interested in by total number of experiments you have performed. That is 7 you are interested in, 7 heads you are interested in. Heads you are interested in, and those turned out to be, and the heads turned out to be, the coin toss turned out to be head 7 times. Okay, so this probability of observing R heads is 7 by 10, that is 0.7. Note that if the experiment were rerun, if the experiment is again carried on, generating a new set of n coin tosses, say second time again you have tossed the coin for 10 times, we might expect the number of heads R to vary somewhat from the value measured in the first experiment, yielding a somewhat different estimate for P. Now, my first experiment, I have tossed the coin for 10 times and I have got 7 heads. So my probability is 0.7 in the first experiment. Now in the second experiment, I have again tossed the coin 10 times and I observed 6 heads now. So the probability of observing R heads here is 0.6. And I performed the same experiment third time, 10 coin toss experiment. Now I have observed 9 heads. So the probability associated number of heads is 0.9. Now what did you observe here? Each of the experiments outcome is different or not? It is not the same always. First it is 0.7, next it is 0.6, next it is 0.9. The event you are interested in is only heads. For that, you got a different probability in the first experiment, different probability in the second experiment, and different probability in the third experiment. Now what did you observe here? The sample's outcome is not the same. In the same way, we are trying to explain you about the sample errors also. The sample errors will not be the same across all the samples. They differ slightly. Okay, the binomial distribution describes for each possible value R from 0 to n, the probability of observing exactly R heads given a sample of n independent tosses of a coin whose true probability of heads is n. Okay, the binomial distribution helps us to tell what is the distribution of the probability across various experiments. if you take different samples with the same number of instances n. Did you understand? Now, interestingly, what do we notice? Estimating P from a random sample of coin tosses is equivalent to the true error from testing H on a random sample of instances. So when you take a sample, calculate the sample error, that you call it as error S of H, the sample error. Now you take the population error. Now this population error, can you compare with P? That is estimating from a random sample of coin tosses. You are estimating what is the probability of P from a random sample of coin tosses. In the previous case we observed, in the first case it is 0.6, in the second case it is 0.7, in the third case it is 0.9. Is there any similarity between the sample errors? No. In the same way, whenever you take a completely new instance from the population, still the true error and the sample error will differ. But our objective should be, the difference should be as minimum as possible. The sample error and the true error, their difference should be as minimum as possible, so that we can say our machine learning model is the ideal model, which is giving very less deviation between the sample error and the true error, which indicates that our machine learning model is highly generalizable. It is predicting well with even new instances also. It is predicting well with unseen instances also, right? Now, a single toss of the coin corresponds to drawing a single random instance from D and determining whether it is misclassified by H. Now, what we are doing is, from the coin toss experiment, I am slowly taking you to our hypothesis. Okay. Now, what is the error, sample error associated with the hypothesis, and what is true error associated with the hypothesis? I'm going to transform this understanding to that area now. Now, the probability D that a single random coin toss will turn up heads correspond to the probability that a single instance drawn at random will be misclassified. Now, in coin toss case, probability D is that a single random coin toss will turn up heads. Okay. Now, if you take, in the case of our hypothesis, it is the probability that a single instance drawn at random will be misclassified. Means you are trying to find out the error associated with the prediction when a new instance is taken from the larger population, and whether your model is performing truly well with the larger population sample also. Truly well with the instance drawn from the population also. Are you okay with these terms? Students, are you able to understand clearly? In the coin toss experiment, you're taking R as the number of heads, probability of observing R number of heads out of n coin tosses. Now come to this scenario. We are taking a new instance from the population and see that whether your machine learning model is predicting that new instance correctly or not. If it is predicting correctly, there is no error. If it is predicting wrong, then there is an error. That is called as true error. Now, whether this true error is similar to your sample error, that is of interest. And if they are similar, then we say that the model is generalizable. If it is highly different, then we say the model is not performing well, or the model is not performing with sufficient accuracy. Okay. Now, the number R of heads observed over a sample of n coin tosses corresponds to the number of misclassifications observed over n randomly drawn instances. We are just relating. Both are different types of problems. We are understanding it in a simplest way and trying to relate it to our complex problem. Okay. So when we take this R number of heads observed when you toss a coin for n times, same problem if you take here with respect to machine learning models. It is the number of misclassifications observed over n randomly drawn instances. Okay, you are interested only in misclassifications so that you can calculate the true error of the model. In the coin toss experiment, you are interested only in heads, number of heads. In the machine learning model, you are interested in number of errors the model makes. Say if it makes R number of errors out of n predictions, then what is the probability of those errors? R by n. Now we are able to relate both of them. Out of n coin tosses, if you observe R number of heads, the probability of observing R number of heads is R by n. Now if you take n predictions made, out of which R are wrong predictions, then the error is R by n. Did you get? Thus, R by n corresponds to the sample error. This is what I try to explain. Sample error is nothing but R number of wrong predictions made out of n number of total predictions made. So, total 10 new instances are given to the model, out of which it has made 8 correct predictions and 2 wrong predictions. Now, what is R by n? 2 by 10. So the probability of observing wrong predictions, the probability of observing wrong predictions here is 0.2 because 2 wrong predictions are made out of 10. Is it clear now? So the problem of estimating P for coins is identical to the problem of estimating true error for hypothesis. Got it now? You are trying to estimate the probability P for the coins, and that is similar to our problem estimating the true error for our hypothesis. Means how good it is predicting with the new instances. Okay, that is what we are interested in. Nothing complex here. It is just being compared with a simpler example so that you can understand. That is why they have taken coin toss experiments example, and that they are relating with this sample error and true error. I'm repeating again, out of 10 coin tosses, if you are interested in probability of getting R heads, it is same as you're taking 10 new instances. Out of that, how many wrong classifications the model would make? That is the event you are interested in, and that we are taking it as R. That is why we can mention the probability of that errors is R by n. That is nothing but 2, when 2 wrong predictions are made out of 10. Got it? Now the binomial distribution gives the general form of probability distribution for the random variable R, whether it represents the number of heads in n coin tosses or the number of hypothesis errors in a sample of n examples. Now I hope it is very clear. The binomial distribution gives us a general description of the probability distribution of a random variable R. In coin tosses, it is number of heads that can be observed in n coin tosses, and in predictions, it is the number of wrong predictions. R would be the number of wrong predictions out of n new instances given to the machine learning model. Right? So the detailed form of the binomial distribution depends on the specific sample size n and the specific probability P or the true error d of h. Okay, so if you want to understand this binomial distribution in detail, it actually depends on the sample size, the number of data points in a specific sample, that is n, the instances, new instances that are being taken, that is n, and the specific probability P, the probability of observing a specific event, either error in the predictions or correct predictions. If we take it as P, then it also represents the true error. This P also represents the true error. True error is the error associated with new instances, the error associated with the larger population. Okay. So the general setting to which the binomial distribution applies is there is a base or underlying experiment, say coin toss experiment, the underlying base from which we can build this hypothesis testing to get the true error and whether it is same as the sample error or not. Where is the base? Where did we start exactly in order to understand this larger complex problem? There is a base or underlying experiment, that is the coin toss experiment, whose outcome can be described by a random variable, say y. If its outcome, say getting a head is 1, getting tail is 0, then y taking head is 50%, chance of y taking head is 50% and y taking tail is 50%, right? So it is unpredictable until you get the outcome. That is why we call the that is why we call y as random variable, which can take two possible values, 1 or 0, head or tail. Now the probability that y equal to 1, that is getting a head on any single trial of underlying experiment, is given by some constant p. So the probability of getting head is p, independent of the outcome of any other experiment. It is independent. Now, when you toss a coin, if you get head, and when you toss a coin next time, getting head or tail is independent of your first outcome. Right? Second time can, because first time you got head, can you say second time also you will get head or you will get tail? Can you say with some confidence? No. That is why we are telling independent of the outcome of any other experiment. Okay. Now the probability of getting heads is taken as P, which is independent of the outcome of any other experiment. And the probability that y equal to 0, that is getting a tail, can be written as 1 minus P. Because probability is 1, probability of occurrence of something is P, the probability of non-occurrence of that is 1 minus P. Now typically P is not known in advance. Nobody knows the probability, right? Until we perform some experiment and assign some probability to it. Typically this probability is not known in advance and the probability is to estimate, and the problem is to estimate it. The problem is to estimate the probability. Until unless we perform some experiment and estimate, expect, guess that probability, we doesn't know about that probability in advance, right? So a series of n independent trials of the underlying experiment is performed. Now say the coin is tossed n number of times, okay, producing the sequence of independent identically distributed random variables y1, y2 and so on up to yn. If we repeat the coin toss experiment n times, then let R denote the number of trials for which yi equal to 1. So what is R denoting here? The number of times head is seen. That is why we are giving y equal to 1 for head and y equal to 0 for tail. Okay. Now we are interested in only heads. So let R denote the number of trials, number of coin tosses for which you get heads in this series of n experiments, n coin tosses. Then how do you calculate R? It is nothing but the sum of all the outcomes where it is head. It is actually simple. This much of explanation is not required at all. What is the final mathematical, what does it represent is the number of times you observe head out of n coin toss experiment. Say you are observing head 4 times out of 10 coin tosses. Then R is 4. Simple. That's all. Now, the probability of the random variable R. Now, what is the probability of observing 4 heads out of 10 coin tosses? Or what is the probability of observing 6 heads out of 10 coin tosses? That is of interest, right? What is the probability? The probability that the random variable R will take on a specific value R, whether it is 4 heads or 5 heads or 6 heads. What is the probability of 6 heads? What is the probability of 8 heads out of 10 coin tosses that are made? Is given by the binomial distribution P of R assuming number of outcomes. Say here we are interested in probability of 6 heads observed out of 10 coin tosses. How can you write that? Total 10 coin tosses. So 10 factorial by how many times you observed number of heads? 6 factorial. R factorial is 6 and n minus r factorial is 4 factorial because 4 times you didn't observe head. So it is 4 factorial multiplied by what is the probability of observing head? P. In a single coin toss, the probability is P. And how many times you can observe that? R number of times, that is 6, because 6 times head is observed, into 1 minus P. The number of times head is not observed raised to the power of how many times the head is not observed, that is 4. This is how you can understand a binomial distribution's mathematical representation. Right? Now the binomial distribution characterizes the probability of observing R heads from n coin flip experiments as well as the probability of observing R errors in a data sample containing n randomly drawn instances. Now you have taken n new instances. Out of that, R predictions are made wrongly. In that case, the accuracy is n R by n. That's all simple. Did you understand now? Now you need not write entire thing in your exam. Just what is binomial distribution? What it elaborates. It tells us about the probability of occurrence of an event, number of times an event would occur out of these many experiments. That is given by the binomial distribution, right? Now in the next coming session, we'll elaborate more on mean and variance and estimators bias and variance associated with them. Now can you quickly tell me what is this error S of H? A general name for this error S of H? Students?
Sample error.
Yes, it is sample error. What is the next one? Error D of H?
True error.
Good. True error. What is E of X? When X is a random variable, what is E of X? Estimated value of X. What is that estimated value of X? It is nothing but the mean of X, average of X. What all values X assumes, take the average of them, that is E of X. What is a random variable? Can you predict the outcome of a random variable? Yes or no?
No. No.
We can't. Yes, we can't predict the outcome of a random variable with 100% confidence. We can't deterministically say with confidence that this would be the outcome of a variable. In that case, we call it as random variable. What is the shape of a normal distribution? What is the shape of a normal distribution? Like this or like this?
Second one.
Second one. It is a bell curve. Okay. Any doubts in today's class, students? Normal binomial distribution you have studied in your PUC, right? Same concept we are just applying to calculating the sample error and true error so that we can easily understand the context. Okay, we'll meet in the next class. Bye.